Okay, so I want to start with a little review from last time. I'm going to go over um, a couple of disaccharides, and I'll talk about how they're built and whether they were reducing sugar or not. Okay, so on disaccharides and oligosaccharides and polysaccharides, the linkage is as important as the actual monomers. In this case, with lactose, we have galactose and glucose. So the linkage is the linkage right here. Um, in the case of lactose, that needs to be a beta linkage since the anomeric carbon, the OH group, hydroxyl group goes up. And then we always connect with carbon number 4 on the right-hand monomer. Okay, so in this case, it's going to be a beta because it's going up. Carbon number 1 hooking up to carbon number 4. Secondly, you've got the second monomer, the one on the right, which is glucose. It is a hemiacetal, this guy here. Okay, and if there's a hemiacetal present, that means it is a reducing sugar. Okay, so you have linkage. You have questions here. Let me okay, so you've got linkage that hooks these two together. What is it? Also, this is an important carbon as well, C6, when we have linkages. Those are the two most common carbons, 4 and 6. 4 by far, like 90%, 9% for C6, and the rest of them are hooking off these other hydroxyl groups. Probably next comes into play 3. Okay, all right, so that's lactose. Sucrose is also a disaccharide. So again, if we look at linkage, and secondly, we look at hemiacetal present or not, which means it's going to be a reducing sugar. Okay, so here we have glucose on the top, fructose on the bottom. By the way, this is the danger, this fructose on the bottom, when you're eating table sugar, because there's an enzyme that will free up these two, producing fructose. It's called sucrase. So sucrase will break that linkage and free up glucose and fructose. Now, the problem is fructose. We're going to talk about that in Unit 5, but it's a particularly awful sugar. It's very, very sweet. If used in moderation, it's okay, like everything in life. But if used in excess, it can cause some major damage to your body in terms of obesity. It's not a probiotic at all. It just does damage. And thirdly, it's also unregulated. So you can eat as much as you want and your body won't say stop. Excuse me. It's a major dopamine inducing monosaccharide as well. So the dopamine, as you're eating this fructose, is going to be being produced, and which ends up being a pleasure center. Okay, so let's look at the linkages on this guy. Okay, with this, we are hooking up not to the C4, or C, in this case, C5, we're hooking up to the actual anomeric carbon on fructose. So there's two linkages now we have to deal with. Okay, the top one is going to be, we're working with glucose, and the hydroxyl group is going down, so that means it is a alpha glucose. Down here, the OH group is going up, so it is a beta fructose. So the linkage is going to be then a alpha 1 beta 2 linkage. Only. If we're going to call this sucrose, it's got to have the alpha 1 beta 2 linkage only. If it's any other kind of linkage, it's not sucrose, it's something else. Okay, the next thing is, are there hemiacetals present? Well, let's look here. Okay, we have two OCOs here. That means we have to identify and evaluate each one as to their, okay, so let's, okay, let's do the bottom one. The bottom one is going to be OCO, so that's a yes. Number 2, is there a hydroxyl group present? No. And is there a hydroxyl, an OH present? No. That means it's a ketal. Okay, let's look at the glucose linkage up here. We have OCO, yes. H present. There's an H right here. So that's a yes. And is there an OH present? No. Okay, so that's going to be an acetal. So we have no hemiacetal present. Now, hemiketals, as I was going through last week, can be converted to a hemiacetal. So hemiketals can form reducing sugars. Okay, so this is not a reducing sugar because there is no hemiacetal present. So no hemiacetal. Okay, you might have heard the word, excuse me, invert sugar. Invert sugar means that the glucose and the fructose present are not linked up. Honey is a good example of that. So honey is healthy in some regard because you frequently will get the local pollen in the area for helping with allergies. But it's not, it has as much fructose in it as sucrose. So it's not healthy from the regard of fructose. So if you eat a ton of honey, you just the same as drinking sweetened iced tea, for example, with granulated sugar. Okay, so invert sugar, all it means is they're not linked up. Same ratio, 1 to 1.
Sorry, can you repeat that word? What sugar?
Invert.
Invert, thank you.
And I don't know where the word invert comes from. It's just, that's the way honey comes. That's why honey's sweet, is you're tasting the fructose. Glucose is not very sweet particularly compared to fructose. Okay, so that's it on disaccharides. Now, when we start adding on more monomers, for example, in this case, it's a trisaccharide. sucrose or trisaccharide. Then we're getting into something called illegal saccharides. Okay, and those are from one to 3 to 10. Excuse me, 3 to 10 monosaccharides. Okay, in the case of raffinose, which is a very important illegal saccharide, it consists of galactose, glucose, fructose. Now, it's hooking up to C6 on this glucose here. And that's a very isolated hydroxyl group. So it's a good candidate for hooking up to, as well as C4 down here is also unrestricted. So that's why you see a lot of C4s and C6 linkages. Man, I'm phlegmy this morning. Excuse me. I guess it's this afternoon now. Okay, so let's look at here. Number one, what are the linkages? Okay, for the top linkage, we have, we're hooking up to carbon number one, the anomeric carbon. And it's going down, so it's an alpha. And it's hooking up to carbon number 6, so it's an alpha 1,6. This linkage here we just went over is going to be, this is basically sucrose here. So that's an alpha 1 beta 2. This is carbon number 2. With fructose, it goes 1, 2. Okay, and the hydroxyl group is going up, so that's a beta. And this over here is incorrect. Should be alpha 1,6. Okay. Now, why I chose this one as an important illegal saccharide, it's a major carbohydrate in human breast milk. So when babies are born, they have a lot of interesting things going on during the birthing process. One is the sharing of the mother's microbiome. Usually the mother has some fecal discharges along with the birth, and that's where the baby can absorb some of those bacteria from the mother's gut. However, what happens though is it needs to be resupplied. So in mother's breast milk, raffinose is part of that. It's not a reducing sugar because there's no hemiacetal. Let's make a quick note of that. And so what happens is the baby cannot ingest and metabolize raffinose. However, its new microbiome in the baby's gut can digest it, and it's considered a prebiotic. So the good news is on breastfeeding, raffinose is supplied. The bad news on formula, some of the cheap formulas out there, raffinose is not supplied in the formula. So the baby tends to not have any of those benefits of solid, healthy microbiome, and they tend to be overweight. They tend to suffer from lots of allergies. It's real huge difference. In the United States, most formulas come with raffinose in it. So it's also the simplest of the illegal saccharides. Okay, if we add another galactose on there, we ended up with something called stachanose. And so we have raffinose. So this part here is raffinose. Add on another galactose, and we have staccanose. So we have two galactoses, one glucose, one fructose. Okay, and it also hooks up to carbon number 6 on the galactose from raffinose, just like when the galactose hooked up to the glucose with raffinose. Okay, so this is going to be just like this one down here, an alpha 1,6, alpha 1,6. This is going to be a alpha 1 beta 2. Now, no hemiacetals. Hence, it's not reducing sugar. And the interesting thing about staccanose, it's a major cause of flatulence. It's a great prebiotic. And this is what happens on dry beans. Now, I cook a lot, and I do like pinto beans and black-eyed peas from scratch. And one of the things that a lot of people don't do is they will soak them overnight or not soak them at all, and they end up with staccanose in the resulting beans. And those may cause flatulence with most people. Now, what you can do to get rid of the staccanose is you soak them overnight and then dump your soaking water. And that will dump out the staccanose. In my opinion, it does not add any flavor whatsoever if you keep the soaking water. Because a couple times before I knew about this, I didn't throw the water away. I kept it in there and I didn't notice any difference flavor-wise after I started throwing it away. And then Beano breaks down these linkages. So you end up with sucrose down here and galactose. So to save money, you don't need to buy Beano, you just throw away the soaking water. Now, there's another type of oligosaccharides, and those are called fructo-oligosaccharides. So instead of the these guys being sucrose, like this guy here, that's sucrose right there. It ends up being a chain of fructoses. Now, inulin is a very common additive to pills and additives, supplements, and it's really used a lot. It's also a nice prebiotic. Bacteria really like it. And there are no hemiacetals, so it's not a reducing sugar. And the N here comes in varying lengths. It's usually a mixture. So you have a terminal fructose, an initial glucose, and you have a bunch of fructoses in between. Okay, and then we can analyze the linkages. We have anomeric carbon number 1 hooking up with carbon number 6 here. And because the OH goes down, it's an alpha, so it's an alpha 1,6 linkage. This is what's weird about this is these are the anomeric carbons. Down here, we're hooking up with an anomeric carbon on the bottom here. But we're not hooking up with an anomeric carbon with the fructoses in the middle. We're using carbon number 6. But the fructose we're using is a beta because the OH, the anomeric OH is going up. We're not hooking up with that though. So here we are. We have a hemi something there. So let's analyze that. Okay, so we have okay, do we have an H present? No. Do we have an OH present? Yes. Okay. So this means when there's no H, that means it's a ketal, either hemi or so this ends up being a hemi ketal. And hemi ketals can morph into an hemiacetal. So these guys are reducing sugars because of that. Okay, when we get to the carb lab, we're going to actually be doing this. You're going to be using Benedict's solution. And okay, so what we have is the blue is the Benedict's solution. So we have maltose, sucrose, and lactose. Now, if you remember, maltose and lactose are both reducing sugars, and sucrose is not a reducing sugar. So when we dump those in, what we end up with is a copper going from, remember, copper plus 2 goes to copper plus 1 during Benedict's solution. That means that's reduced. So the maltose is oxidized and the C plus 1 forms this orange jump here. So that's positive. And because sucrose is not not a reducing sugar, it does not expose any aldehydes. So what happens is there's no way that the copper can be reduced to copper 1. So there's no reaction here. Okay, here's a quick rundown on the disaccharides linkage-wise. Okay, so what I want to do is look at I'm going to look at let's see, let's look at lactose. Okay, lactose is galactose and glucose. So here's okay, so that's galactose. So this is galactose. Okay, and when galactose and glucose form a glucose, form a disaccharide. This hooks up these two together. And notice that this is a beta galactose. And in this case, this is a beta glucose. So a typical test question is I'm going to give you, for example, lactose already linked up. So that's what this looks like here. Okay. So that's beta lactose. Okay, it's beta lactose as opposed to alpha lactose because of this hydroxyl group here on the right is going up. Now, these are questions I would ask. What is it? Well, it's lactose. Okay. What's the linkage? Okay, it's going to be a beta 1 for linkage. Reducing sugar. Well, is there hemiacetal present? That's a hemiacetal. It's got so yes, because there's a hemiacetal present. Okay. Number 2, what test would you use? Okay, there are 2 tests, Collins and Benedict's. When we do the lab, there's a couple more tests you can do also. But for right now, in Unit 2, we're talking about Tollens and Benedict's. Okay, let's do Tollens, because you've done Benedict's more than once before. Okay, so let's look at Tollens. Tollens is silver, cation ion, goes to metallic silver. And then the exposed aldehyde from the hemiacetal is going to be oxidized to the acid salt. So we're going to start with our lactose, and it's going to open up right along the hemiacetal there. Okay, so that's the aldehyde. That's what's going to get oxidized. So that's going to be converted to the acid. And because it's in a basic environment, it's going to be oxidized to the acid salt. Okay. Now this is pretty much, notice I didn't put a double arrow there. This is pretty much a one-way deal. Okay, so what we're doing is we're adding Collins reagent has silver nitrate in a basic environment. And the basic environment is what pulls off the H off the acid part, making it an acid salt. So what happens is that Ag plus goes to Ag0, or the metallic silver. And then, so that's reduced. And then this is oxidized. So you always have to have both of them going on at the same time. Oxidation, reduction. Okay, so that would be the test I would use to test whether this is a reducing sugar or not. And what happens is this turns into a mirror. Turns into a mirror on the inside of the test tube. And by the way, this is how they used to fix antique mirrors. And antique mirrors used to be silver coated. And when the mirror gets old, it frequently, the corners of the mirror, the silver metal will flake off. And so to restore that, what we do is we do the tolerance reagent on that glass part of the mirror. And then this mirror, the silver mirror, plates onto the glass mirror on the back. So that corner is restored. So it's a very common technique for fixing antique mirrors. Okay, so this is the guts of this reaction. Where we have the aldehyde going to the acid salt. The silver +1 goes to silver 0. Okay. And really, this is the that's the only reaction here. Everything else just tags along. Okay. Okay, so these are the typical questions I would ask. I would give you the structure and I'd ask you for, what is it? And make sure you say alpha or beta for a lactose, alpha, beta for maltose. Because they have that hemiacetal can go up or down. Sucrose doesn't have a hemiacetal, so it cannot go up or down. So sucrose is neither alpha or beta because there's no hemiacetal. All right. Let's see. Now on Wednesday, I'm going to go over a practice test with you, and I'll show you what the thing looks like, etc. And remember, you can have 2 3x5 index cards, both sides. Okay, so we get into the polysaccharides. We're just adding on more and more monomers, usually glucose. Sometimes when this N gets really large here in the inulin, we can have a whole bunch of fructoses. But the most common polysaccharides are made up of glucose. Sometimes they're really large too. What's interesting about polysaccharides, um, they're not all that soluble in water. So to thicken something like a gravy or something like that, you mix it up in cold water, not hot water, because the cold water will disperse the polysaccharide. And then as that happens, all the hydroxyl groups on the glucoses will start to pick up and do hydrogen bonding with the water. And that's what makes the starch water tends to really thicken up because it's binding with the water. Not the same as solubility, though. It's really kind of that's why they call it a colloidal dispersion. Um, Now, the interesting thing about there's a couple of them. Starch is everyone can relate to starch. Most commonly used one. And the thing about starch, it's just a long glucose monomers, thousands, thousands. If it is unbranched, it's called amylose. Alpha 1,4 glycosylic linkages. Now, on polysaccharides, there's always an end unit, a terminal monomer. In this case, the monomer, everything is glucose, so this is what the terminal monomer looks like. That is a hemiacetal. We have OCO, anomeric carbon, OCO. Hydrogen's present, OH is present, so it's a hemiacetal. So, question is this a reducing sugar or not? The answer is yes. Why? Because the terminal monomer is a hemiacetal. So I'm calling it weak because in relation to the thousands of non-hemiacetal monomers, it's 1 in 1,000. So its effect of being a reducing sugar is minimized, but it's still a reducing sugar because of the terminal glucose. Sometimes there is a branch on carbon number 6. So we have unbranched, branched. So we're going from anomeric carbon number 1 to carbon number 6. It's going down, so it's alpha. Hooking up with carbon number 6. Amylose, amylpectin. As a test for starch, frequently they use iodine. And what happens is the iodine physically gets into the helix form of the starch. Now, the helical formation versus a long string of glucoses is more stable. You'll see that when we get to a DNA and RNA, same thing. The first level of organization is a long string. The second level of organization is a helix. And there's plated, or excuse me, there's pleated and helix as a secondary structure. But with starches, it's usually helix. And the iodine is bound up inside that helix coil. Now, the only polysaccharide mammals make is called glycogen. Glycogen, again, is the same thing. It's a whole bunch of glucose molecules, but it's very highly branched. Amylpectin is not as branched as glycogen. Amylpectin comes from plants. Glycogen comes from mammals. They're almost exactly the same, except the glycogen is more branched. So this is a way the body stores energy. One of the ways. The other way is storing it in fat. Using glycogen as an energy source is much quicker than fat. When you use fat for energy, you have to take the fat apart and then form glucose. So there's a lot of steps there. Where this is one step to free up the glucose. One step. You're just hydrolyzing off a glucose. So the energy is much quicker. So when you work out, you store glucose in the form of glycogen. It is normally stored at the site from which the exercise is going on. For example, you're doing curls. Okay, that means you're using your biceps big time. So when you do a lot of curls, you're storing glycogen in that muscle. You're also storing glycogen in your liver. So what happens when your biceps need energy, it doesn't have to go to the liver to get energy. It goes right to the muscle where it's stored and hydrolyzes that glycogen to glucose. So it's readily available, much quicker, a lot quicker than getting it from fat, but also quicker than going to the liver to get the glycogen and hydrolyzing it. Okay, the other common polymer is cellulose. Cellulose, again, is just a bunch of glucoses, only the linkage is what's different. Okay, in amylpectin and amylose, the linkage is a 1,4, alpha 1,4. In cellulose, it's a beta 1,4. That's the only difference. Our body's enzymes don't recognize the beta linkage. However, our microbiome bacteria do. So by eating fiber, we're actually feeding our microbiome bacteria. Additionally, the fiber reduces the time it takes to digest your food. So it aids in that way. So your liver's not, or your pancreas is not spiked for insulin requirements. So it's a lot of favorable things to do consuming cellulose. So it's considered a prebiotic. Major microbiome. Okay, so that is it on carbs and alpha or aldehydes and ketones. Now, the thing I want to stress is the reactions are not hard. What makes them complex are the structures. So I want you to focus on, going back up here. So we have a hemiacetal produces a aldehyde when that ring opens up. So now we have an aldehyde reaction. Aldehydes are readily oxidizable to an acid unless it's a basic or alkaline solution, which you end up with the salt of the acid rather than the acid itself. And then whatever agent is the oxidizing agent is reduced. In the case of toluenes, it's A plus. In the case of Benedict's, so this is toluene. So in the case of Benedict's, we go from copper plus 2 to copper plus 1. The aldehyde does the same thing, so also in a basic environment. So try to net this stuff out so that you don't get this uh, the baggage that carbs add with all this structure, because the reaction itself is very similar to what we studied in the aldehyde ketone chapter only. Okay, that's what I wanted to cover today. Now these you need lots of practice. Are there any questions about what we've done today? So we look at files, Canvas, Unit 2. There's some additional worksheets that I've provided. And this one has the answers as well. Hopefully the answers are all correct. I've been known to make occasional errors. Okay, so I encourage you to print those off and practice that some more. Okay, there any last minute questions? You all
I had a question, Professor. I'm so sorry. I wanted to know, will you be publishing an assignment tab to be able to submit the lab 5 that we did last week?
So there's no assignment for that?
Well, there is, but you have to go inside of the modules to find it. Because I usually just go through the to-do list on Canvas, and then that's how I do my assignments. So I didn't know if you wanted us to go look for it or you're going to publish it to the to-do list.
Okay, so I just did What was the one you're talking about? Lab 4, lab 5?
Wet lab 5, the one that we did last week.
Oh, okay. So it's going to be due Wednesday. Okay,
Thank you.
so if you go to assignments, you should see it.
Okay, thank you.
You're welcome. Thanks for pointing this stuff up. I've got 100 students and juggling all this stuff. Sometimes the assignments get out of date because I have to import them from another class from a previous semester. So what it does is it ports over the due dates also, which of course are out. So I can either turn the due dates off, which means that no assignments have due dates, and I have to update that, or if I don't import the due dates, if I do import the due dates, I just have to update them. So it's one or the other, but I still got to update the due dates for the current semester. So if you just remind me, I can do it really fast. I just have to do it. So, and if by chance I didn't do it and you submitted it and it was quote unquote late, I won't deduct any points. Yes, test 2 is next week, not this week. So this Wednesday, I'm going to be going over practice tests and just example problems. Okay, so Bianca, does that make sense? Cool.
Really, I want to relax.
Professor, I have a quick question
Like
about
that.
the wet lab for the SAQ. Just to
I
be
want to relax in my iPod in my brother's room, and he fucking
It's,
sat in the
uh,
dark for like 30 minutes until he fell asleep.
Nick, do you mind? Maybe. Sorry.
Okay, so ask again, please.
Yeah, sorry. So just want to confirm in the SAQ, there was Don's soap. I looked into like the specifics of it, and they had like a mix of like three different chemicals, but they only had like one first aid measure. Should I list the chemicals in there, or should I just put Dawn soap and that's okay?
For which lab? The soap making lab?
No, no, lab 4, the steam distillation. I just want to make sure that I got the SAQ correct because like it has like I'm looking at the thing. It has three different like multiple chemicals mixed in, like sulfuric acid, sodium salts, etc.
Yeah.
Should I just put Dawn soap and that's fine, or should I list out all the chemical names?
Well, some of them, the sulfuric acid, for example, you just say C lab 5.
Good to go. Yeah,
And then if the state is the same for each one,
yeah.
don't repeat it. Just
Okay.
put the chemicals at the top. Does
Okay. Thank you, Professor.
that make sense?
Yes, it does.
Because remember, I want you to be safe, but I don't like busy work.
Understood. Good to go.
That's what we're trying to do here.
Yeah.
Because these labs can be really long, and I don't want to add. Also, some people are doing their labs in pencil, and I didn't want them to copy it over. I just said, just the next lab, do it in pen.
Thank you, Professor.
Sure. Were there any other questions?
Lab's over. Breakfast over already?
I'm sorry, what?
Oh,
Yeah, we just got lab at 3. That's it.
Okay, I don't know if that was directed towards me or not. What? Okay. Now the lab today is a pretty good lab. It's you're gonna actually be doing you're gonna taking the zest of 4 oranges, no pith, nothing white on there. And these oranges I want you to take home with you because they're perfectly good oranges to eat. You have to consume them probably in 24 hours because the outside will get dry, but taking the zest of an orange doesn't do anything in terms of the inside. And if you want to eat them, You can zest them out in the hallway, and do not throw any peels in the lab garbage. All peels go out in the hallway compost. The reason for that is if we get audited by OSHA, they will look in our garbage cans in the lab to see if there's any food in there. And oranges, they're going to see orange peels in there, and they're going to say, oh, these students are eating in the lab, which of course is not allowed. So that's what I'm saying, throw your peels out in the hallway. That goes for candy wrappers or anything food related needs to go outside. And if you see any food related wrappers in the garbage in the lab, let me know and I will write up the previous lab instructor. Excuse me. Okay, so Edgar, you said, is it a unique practice test or is it already on campus? I don't know. I need to check. Um, There are amino acid practice tests here, and that's from when I only had 3 units. I included the carboxylic acid unit as far as unit 2, but you just skip down to there's one on ketones and carbs. So there are practice tests that already exist there. Some of them have keys, some of them don't. This is a hodgepodge of all the units. Well, anyway, there are some practice tests there. And I'm going to be going over 1 or 2 of them on Wednesday. Okay, so does that answer your question okay? Okay, I'm presuming that's a yes. All right, any other questions? Okay, well, I'm going to end this, and I'll see Monday folks in a little while.